There we go. Okay, so I have two different ways to give you guys this sort of information. I wanted to spend a little bit of time of going over some experimental stuff and then going over some pre-response questions that cover it, because we know that that's partly how they intend to do these questions, is base them on experimental settings where you have to like look at or analyze data in some way. So I've got this PDF was linked in the weekly plan itself. And then I also have a presentation that takes this document and then intersperses practice free response questions in with it. So for people who are watching this later, or you want to go back through some of these things, you may want to look at the presentation that's linked at the bottom of the plan, just so you know. So this first experimental procedure is something we did last year. And by last year, I mean in honors chemistry, not in AP chemistry. And I never use the word gravimetric analysis, but it's exactly what we did. Like, you mix stuff together, you make a solid, you filter the solid, you dry the solid, you weigh the solid. Like, we did this. And you know, these are your basic steps. So you can do it where you're mixing two different liquids, but you can also do it where you're dissolving a solid and then adding another liquid. So there's several different ways to do it, but essentially it's all filter a solid precipitate, rinse it, dry it, weigh it. The most common mistake when you do this is that your stuff isn't actually dry. And if your stuff's not actually dry, your mass is going to be too heavy, right? Because you've got extra water in there. And if you've got extra water in there and your mass is too heavy, then your percent yield is going to be too heavy. So one of the things that I want to point out in this entire presentation is they do a good job of going through and saying, if something happens, this is the effect it will have. It'll have on your actual lab results, because we know that often that question is, so would your thing be too big or too small? Would it stay the same? So this is specifically saying your percent yield would be too high if your stuff was wet, right? So you may want to have this document handy on test day, just in case they ask a question like that. It could be an easy, good reference for you. Let's see here, blah, blah, blah. Net ionic equations are normally something they ask when you're having to do this, as you'll see with some of the practice problems we're going to do today. So that's gravimetric analysis. Making a solution. While they've asked about making solutions in the past, I don't think that with a condensed test, this is something they're going to ask about, because it's kind of a randomly small little technique, and it's not something that generates data, right? Gravimetric analysis generates data that you could actually be asked to analyze in a question. Making a solution does not. But regardless, we know making solutions involve the volumetric flasks. And as long as you remember that the volumetric flask is only used at the actual like mark that's on the flask, and it only measures one volume. So that's the main thing to remember about solutions, or even dilutions, which is another thing. Titration. I think titration is a good possibility for being on the test, because it generates data, and because they basically ask about it almost every single year. So it's clearly something that they care about. And again, we went through the terminology before, but we have the terminology like analyte, or what you put in the flask. And then we also have the titrant, which is what you put in the burette. And the whole point of a titration is making the color change so you know when to stop. And when the color changes, what that means is you have equal moles now. So that's what it is you have to do. So the most common mistake is overshooting your titration and making your color change too dark. And if you overshoot, that means you're gonna think that you have a higher concentration than you actually do. And that would be a bad thing. So that's the most common mistake with a titration. You can also like literally forget to put an indicator in. That is a dumb question because they can't really ask you how that would affect your results because you would basically have no results, right? Like you don't know when to stop if there's no indicator. So the most common thing they would ask about is this first situation and ask you if you overshot, if you put in too much, what would that mean for your resulting calculations? Let's see here. We can use it for both acid-base reactions and for redox reactions. We only did an acid-base titration. The example we're going to do today is a redox titration. It's the same thing, right? It just happens to be that redox reaction, oxidation reduction reactions, change color on their own without the use of an indicator. Like they just do that on their own, and therefore you can tell when to stop that way. Definitions, all sorts of stuff there. So if you don't remember the titration experiments that we did, go back and look at that. Beer's law and spectrophotometers. We did multiple labs with this in the fall because this is another experimental technique that they like to use. It generates data. Most of the time that data is graphical and you have to analyze a graph. So, but remember, we were figuring out like colors and colored solutions. And the main thing is that spectrophotometers, this technique only works with a colored solution. It only works with a colored solution. It only works with a colored solution. So there's a lot of metals that don't make colored solutions and therefore they would not work. But your irons, your coppers, your leads, your chromiums, things like that that make colored solutions, this works well for. And in fact, we did it with copper solutions, those blue solutions. We also did it with the crystal violet, which was a purple solution. I had you hand draw graphs, these concentration versus absorbance graphs. They're clearly not going to ask you to do that, but there is a possibility that they might provide a graph for you that you would have to analyze. So that is another way that they could make you do something with data. Again, pretty much the only mistakes you can make is doing something with your cuvette. I don't know if you remember, but I constantly ask questions in all these labs. What would happen if your cuvette was too low? What would happen if you filled your cuvette too high? What would happen if you have fingerprints on your cuvette? What would happen if you have water droplets on your cuvette? All these sorts of questions, because that's the main way that you can mess up spectrophotometer work, is doing that. And that's all listed in there, blah, blah, blah. So that's all that. Chromatography, I can pretty much guarantee that I don't think they're going to ask a question on this because it's so not used very much. Paper chromatography, there was a question 4 years ago. I don't think this is the year to bring back a question, so I'm not going to focus on this, but you can go back through it on your own if you want. I think this year would have, on a regular test, would have been a good year to have done chromatography, because sometimes they cycle these things every 5 years or so, but not with a little short test. We're not wasting time with a little short test for chromatography. Same thing with distillation. I don't think they would ask you anything about the process of distillation. I think it's possible that they could ask you about lower and higher boiling points and vapor pressures, but they don't need to talk about the actual process of distillation to be able to do that. And we answered these questions when we were covering Unit 3, and that made sense to you guys there. So, so I think that's that's all good to go. Calorimetry. This is the other good possibility for lab techniques. So gravimetric analysis, titration, and calorimetry, I think, are the most likely options for experimental techniques that are going to be on here. Mostly because coffee cup calorimetry is an easy procedure to do. It's one that most people do in their classes. We've done it multiple times. And it also just generates easy results that you can do all sorts of other stuff with. So we did this year and last year. So remember, you've got stuff in the cup. You are measuring the liquid in the cup. The liquid in the cup is water, and the liquid in the cup is the surroundings. So one of the things you're always going to have to remember is flipping your sign. You need to remember the difference between exothermic and endothermic, right? So if your temperature goes up, it's exothermic. If your temperature goes down, it's endothermic. And then you need to make sure that you remember how to deal with the masses, all this sort of stuff. But I will say they have in the past shown like a very simple graph of the temperature change, and you had to read the graph and state whether it was exo or endothermic, and then do the temperature, actually calculate the temperature change and say, is it a negative temperature change or a positive temperature change? That's a possibility for this year, because it would be an easy way to do some easy points and then have to do a basic calculation and then state some other stuff. So if you don't remember having done coffee cup calorimetry, this is another experiment to go over. Again, I don't think they're going to ask about dilution on a shortened test this year because it doesn't generate data. So we'll not worry about that. Gas collection over water, they could. We did this experiment. There's not a whole lot to do here. The only thing you have to remember to do is to subtract off the vapor pressure of the water that's in the bottle. And that's just subtraction. So there's not a whole lot to do, but like we literally did this experiment on the left in class. That was the first lab we did this year. And let's see here. Hydrate percent composition. This is another thing that could generate data. They haven't asked about it in years because it's kind of such a basic thing. You can't do as much with it as you can with gravimetric analysis, but it's basically, it's another form of an empirical formula lab. So remember, we actually had a setup very similar to this when we did the magnesium and the oxygen burning off in the crucible in sophomore year. So you have access to this file. This is just a PDF. And then I was saying I also have a blah, blah, blah. I also did a linked to a lab procedure review full presentation that goes through the entire thing. So if you want to go through this on your own as well, and it goes through all the pictures and then like the tips and all that sort of stuff. So this is also linked at the bottom of the weekly plan. But really I wanted to focus on two questions from last year's free response questions, because they were both lab-based and I think very similar to things that might happen this year. So this is what I had sent the other day, I believe. I think I did. Yes, sure. Water. Okay, so this first question was a long question, question 3. We're only going over the first half of the question because the back half of the question now covers stuff that is no longer going to be on the test this year because it's out of Unit 8. But they start off by saying, A student's given 50 milliliters of a solution of unknown concentration. Okay, so clearly if the concentration is unknown, you can already guess that at some point they're going to ask you to figure that out.
Yes.
That's kind of the whole point. So it says to determine the concentration of the solution, the student mixes the solution with excess 1 molar calcium nitrate, causing a precipitate to form. And remember, precipitate just means a solid. And then they give you the balanced equation. So balanced equation means I'm going to have to do a mole ratio somewhere. So what this process is describing is gravimetric analysis, right? That first lab procedure. And basically you know that because anytime you have a precipitate, that's what you're doing. So precipitate is going to mean you want to filter, you want to rinse, you want to dry, and then you want to weigh. That's the entire point of making a precipitate. So my solid precipitate, they're not even asking you what it is. They tell you what it is. It's right there. It's the solid. So my precipitate is the calcium carbonate. And in the lab we did in class, the precipitate was also calcium carbonate. That's what we did. I think I used sodium carbonate and I think I used calcium chloride instead of calcium nitrate, but you guys essentially did this exact same reaction in class with me 2 years ago. So part A, write the net ionic equation for the reaction that occurs. This is still fair game to ask on this exam because you can do a net ionic. So if we're using my easier method of figuring out a net ionic, what do we immediately move down into my net ionic equation?
CO3?
The CaCO3.
Yeah, that's solid. I feel like that's a solid choice.
So the net ionic is always basically what makes the solid and work backwards. So that's the thing that makes the solid. So what needs to be on the reactant side?
Ca and CO3.
Okay. What do you have to remember to put with those?
The charges.
The charges.
Yeah.
Okay. And what is the charge of each one of those?
Is Ca 2 plus?
2 plus. So CO3 is? 2 minus. Yeah, somebody said it.
Yes.
2 minus. So net ionic equations are not correct if they don't have the charges. They don't care as much about putting the AQ symbols in. So they're not going to take off points if you don't have the state of matter symbols on a net ionic equation. They will take off points if you don't have the charges. So if you need that polyatomic ion chart, again, if you don't have yours with you, let me know and I can send that out. So, but that's the net ionic equation. I can pretty much guarantee on one of these two equations or one of these two questions next week, they're going to ask you to write a net ionic equation. And it'll be worth a point, but it should be a point that you get because we can do that. Part B says the diagram below is incomplete. Draw in the species needed to accurately represent the major ionic species remaining in the solution after the reaction has been completed. Okay, so this is what we would call a particle diagram. And in a particle diagram, we always need to make sure that we count things. And that we keep any ratios, right? So any ratios from a balanced equation, from a formula, from a charge, anything like that. So if I've got solid calcium carbonate at the bottom, What needs to be in this solution? Count stuff. What do we have?
We need 2 more sodium.
All right, why do you say we need 2 more sodiums?
Because the ratio of sodium to NO3 is equal in the balanced equation, but it's not equal in the drawing.
Okay, so I don't have a balanced number of positives and negatives in this thing, right? However, do I need more sodiums? Is that the thing that I actually need? And this is why this was a harder question. It goes to what we marked up here in blue at the top.
Do you need the NO3 or the C8? Because it says you put excess. So
You're
you
right.
just do with that.
So that's what I had in excess, was the calcium nitrate. So I have a limited amount of sodium and a limited amount of carbonate. So all of my carbonate is down here, because that's the whole point of this process. So all of my carbonate is down there, which means that these are a limited amount. I can't have more sodium because that was a limited amount. But you are correct that the first thing Carl noticed was that there is not a correct ratio of positives and negatives here. So I have right now 2 extra negatives. So in this drawing, I need a single calcium.
Yeah.
Because the calcium is in excess. And really it's the calcium and the nitrate, but it's already showing you nitrate in excess. So what it was missing was the calcium in excess. So that's all they were looking for there. We know they're not going to ask you to draw a particle diagram, but again, they are most likely going to ask you to analyze one at some point. Okay, so there's my data. All right, it says the student filters and dries the precipitate of the calcium carbonate. They give you the molar mass, which they are doing more and more to try and speed along the process in these questions. And they give you that data table. And then the question says, determine the moles of sodium carbonate in the original solution. What number do you start with there?
You start with the volume.
100.1 grams over something.
Oh, I wish we did. Nope. Because
volume of the Ca and NO32.
for the moles of sodium carbonate, where is the carbonate in that data table?
With the carbonate is with the mass, or it's with
Yep.
the 0.93.
That's where the carbonate is. So that's where you have to start. Yes, it's up here, but it's only a volume. I don't know a concentration for that 50 milliliters. So that doesn't help me, right? So my carbonate is all in this calcium carbonate. So that's where I start. That's also why they gave you this number. This number right here is an indication that you're going to use that in this first part. They're not going to give you information that you don't need. I will say that. They've at least stopped doing that. So for C, you are going to start, and anytime you have a a gravimetric analysis where you make a solid and you weigh it and you do all that sort of stuff, you are going to start with that amount. That is the actual important thing. So you'll start with 0.93 grams calcium carbonate, convert it to moles with the molar mass they gave you. And if they want moles of sodium carbonate, what's my last step?
Use the mole ratio.
Use the mole ratio. So what is the mole ratio though? Calcium carbonate, sodium carbonate?
1 to 1.
1 to 1. How easy. All right. So this is a 1 to 1. So 1 calcium carbonate, 1 sodium carbonate. And you would do that, and it's going to be a small number. How many significant figures will that number be?
2.
2.
So 0.0093 moles sodium carbonate. Box your answer for the old people. Okay, now these next two questions are what we refer to as lab procedure questions. They're asking you, how do these things that this person did or thinks, how will that affect various aspects of your answer? So for D, it's the student realizes that the precipitate was not completely dry. So if it's not completely dry, what does that mean for this number?
Means that it should be higher, or it would be higher.
All right, so that means it would be bigger. Okay, and then it claims that as a result, the calculated molarity is too low. So do we agree with that and then justify? So do we agree that a bigger number here would give you a molarity that was too low?
No.
So wait, Ms. Baskin.
Yes.
So it's saying, like, okay, so let's say I put a bigger, like I put like, I just put a bigger thing in where we started for C. That's what it's saying?
Yes.
Okay. So
So
then
if
I
I
would
have a
put
bigger number there, what does it mean for my number back here?
It's bigger too.
All right, and then,
So then the molarity would be bigger, right?
right, so then the molarity would be bigger because the molarity is just that mole amount divided by 50. So a bigger numerator is going to just be a bigger number. So do we agree or disagree?
Disagree.
We disagree. And the reason we're going to say that we disagree is that the not dried means extra water in the precipitate mass. So it would be bigger mass, which would be bigger moles, which would be a bigger molarity, because moles is in the numerator. So most of the time when they ask a question like that, they are asking you to basically walk back through a calculation you just did. All right, it's not typically an unrelated calculation. So you just did the calculation in C, and they're saying, we're going to tell you this thing, this not completely dried thing. You have to decide, what does that mean for this number, what does that mean for your calculation for this number, then for the thing that they ask. So it is always appropriate in these situations to walk them through what it does step by step in the calculation you just did, right? It would give you a bigger mass to begin with. That would then lead to a bigger moles. That bigger moles, since moles is in the numerator, would lead to a bigger molarity. I disagree. Does that make sense?
Mm-hmm.
Cool. All right, and then E. E is saying after the precipitate forms and is filtered, the liquid that came through the filter is tested to see if it can conduct electricity. What is needed to conduct electricity?
Ions.
Ions. You need ions. Okay. Would the solution that ran through the filter have ions in it?
I'm confused.
Why?
Yeah.
What solution is this? What liquid is this? It's
Yeah.
the one that we have left.
It's that.
See, but they weren't specific.
Yeah, they were.
Oh, yeah, they were, because you were trying to get the precipitate.
Uh-huh.
Oh,
And it says
yeah,
specifically that this is remaining in solution. After
Yeah,
it's everything
right.
is completed, it's remaining
I
in
feel
solution.
like for everything they try to explain, when they just say liquid or they say, I'm like, what you mean liquid? Every
Right.
other time you're going to tell me what the liquid is.
I know.
But they kind of did.
So here, basically, right, this is, and I don't know if you remember this when we did it, but we had the same thing. We have a beaker and you dumped the stuff together and we ended up with a solid in the bottom and we had all this solution. And this is what you dump this into the filter, right?
Yeah.
This is what you dump into the filter.
Mm-hmm.
This stays in filter. And this whole solution here is what runs through the filter and ends up going into the flask. So for us, we used, a poor man's funnel. And then we had the flask like this. So the solid ends up being in the filter, and then the solution behind it is what has all of the ions and stuff in it. Right? So for us, what would be observed? Would it conduct electricity? Yes.
Yes.
It would conduct. And it's simple enough to say it would conduct because there are ions from the excess, that should be an E, from the excess calcium nitrate solution that was added. You could even be cheeky and say, as seen above in your diagram.
Oh, yeah, I would say that.
Mm-hmm.
I love doing that on these AP exams.
Yeah.
As very obviously stated by the diagram.
But again, seen in your diagram above. But again, part of the reason that they gave you that diagram is because it was linked into a later question. So it's not that they give you extra information that you don't need, it's that they give you so much information that you forget that it can apply to multiple places. Okay, so this was a long question. And then question 7, which was the last question on the test last year, was yet another titration question. You know it's a titration question because they give you a picture of a damn burette. So there it is. I mean, you can turn the page and see this and be like, oh, I guess I know what's coming. They give you a balanced equation at the top. So they're already telling you, I'm going to be using a mole ratio somewhere, because otherwise you wouldn't tell me that thing. And then start looking at the words. So a student dissolved 0.139 grams of oxalic acid, and they give you the formula for it. And that's this thing. In water in a flask. the student then titrated, so they're telling you that that's in the flask, right? And then they says they titrated the solution with KMnO4, which has a dark purple color. So that means that this stuff is dark purple. Okay, and the balanced chemical equation is given above. Now, my question again, where is the potassium in this equation?
She's a spectator.
She is a spectator. So we do not have her. So you can just cross her out. And now you see that the permanganate is this guy. So I can already see that my mole ratio is a 2 and a 5. Okay. So A, identify the species that was reduced. So reduced means what happened to my oxidation numbers?
They went down.
They went down. Okay. So in this sort of thing, I can tell you what it's never going to be. It's never going to be the oxygen and the hydrogen. It's always going to be the other things. So you really only have two options. It's either the manganese or it's the carbon. Which of those seems easier to figure out first?
The manganese.
The manganese, because it's already telling you that it's a +2 on this side, and you only have to figure out what it is in the permanganate, whereas in the carbon, you got to figure out what it is in both the CO2 and in the middle of that oxalic acid. I don't really want to figure out the carbon oxidation number between the hydrogen and the oxygen unless I have to, because that takes more time. So for my MnO4, what do I get to automatically assume?
The oxidation of oxygen.
Yes, so I get to assume that the oxygen is a -2, leading for 4 of those, a total of -8. I got to remember to leave 1 left over, so the manganese is a positive how much?
7.
7. Okay, so was the manganese reduced?
Yes.
Yes. All right, so I get to say that the manganese, it went from a +7 to a +2. Done. Then the next question says the student used a 50 milliliter burette, which is what you guys used, to add the permanganate to the acid until a faint lavender color was observed in the flask. An indication that the end point had been reached. The initial final and final volume readings of the solution are shown below. Write down the initial reading and the final reading and use them to determine the volume of permanganate that was added. They're literally going to give you a point for reading this piece of lab equipment. That's a good thing. So what would we say the volume is for the initial?
Okay, wait, Miss Baskin.
Yes.
When reading this, right?
Mm-hmm.
So you can see on the first one, what is that? So they zoomed in, praise God.
Yep.
3, 4, 5. So that's 5. Or no, wait. 3. Oh, it's like 3 point something, right?
It is 3 point something. So that where I just drew is the 0.5 line.
So was it like 3.3?
3.3 what though? Because it's between those two. 5.
Jesus.
Right? So for us on these burettes, if the meniscus here is between 2 marks, call it a 5. Right? So 3.1, 2, 3, that's 4. It's between the 3 and the 4, so we're going to say 3.35. So it is also between 2 lines on the final. So what are you going to call that one?
29.55.
5.5.
Yes.
Right, because it's between the 5 and the 6, so it's a 29.55. So I've got my initial, I've got my final. So what volume was actually used?
26.2, I think.
Mm-hmm. Bam. Okay. And then it says, given that the concentration of the permanganate was this, so I've got a volume and a concentration, calculate the moles of permanganate ions that were used. That's a one-step problem.
Mm-hmm.
All you guys to do is multiply the two things together. So 8.0235 moles per 1,000 milliliters.
Mm-hmm.
And it would have 3 sig figs. And it's going to be a tiny, tiny, tiny number. And for this sort of thing, they don't care if you put it in scientific notation or not. If you wanted to stick the zeros before there, that's fine. All right, and then part D is another lab process question. It says the student proposes to perform another titration using a 0.139 gram sample of the acid. How much was the original sample? So this is 0.139 grams. And up here we were also 0.139 grams. So, all right, so we're still talking about the same mass. So that's good. Okay, so that's the same mass. But this time using that concentration. How does that concentration compare to that concentration?
It's smaller.
How much smaller? Is it like half as much? Is it?
It's a little bit more than half as much.
Can you just subtract it to find out?
No, you should divide it to find out.
Okay,
Right.
Thank you, math teacher.
0 divided by, and you'll find it's 50 times smaller. 50 times smaller, not,
Whoops.
or 16 times smaller, sorry. It's not half, it's half, see, because it's not, it would be half if it was 0.0143, but it's that much again, that extra zero in there. So it is way smaller concentration, right? Way smaller.
Yeah, that's the term I'm gonna use on the
Way
test.
smaller. So would that concentration be a reasonable choice to use?
No.
No. How much? We're using the same mass here. We basically used half of our burette with this concentration. So the answer is no, it would not. No, it would not. Because the concentration is so small that you would run out of solution in the burette. And there's practically nothing worse in a titration than running out of solution in the burette. The only thing that is worse is to forget to put indicator in and therefore not knowing when you're supposed to stop. But that's why, like, when we did a titration, right, we did that first fast and dirty one so you would know about how much you would use so that you could see, like, what you need to have in your burette to be able to do the others. So I expect some form of a titration question, and I expect some form of a gravimetric analysis question, and possibly even a calorimetry. Those are my 3 lab procedures that I think they are going to ask you about. So again, the PDF that went over those procedures is linked in the plan. The presentation that goes over them in more depth is also in the weekly plan. The actual solution guides from the College Board for these 2 question portions are linked in the plan. And then the last thing I need to do for you today is I need to make those the annotation video, which I have not done yet, and I will send that to you. So my plan for next week is they just released some official practice questions. And I want to go over those official practice questions on Monday. And then Wednesday, we could just do a check-in and be like, anybody have any last questions? Anybody have any like technical issues? We good, we good, we good. And then I double check with Ms. Shaw and Pascucci to make sure we're all on the same page, but none of us are really planning on doing anything after you take your exam next week. So we're almost done meeting and almost done with everything. So there you go.
Mm.
Yeah.
Yeah.
Have people actually tried the demo site?
No.
No, you need to do that. You need to decide how you are going to submit stuff. You need to practice to make sure that you can get a submission in under 5 minutes between taking pictures in your phone, converting to PDF, getting it to your computer, and uploading.
And okay, so for the demo site, did you send out in the plan, or did they send out in an email?
It's in the plan. Probably both. I'm sure they sent you an email too. But
Okay,
it's
cool.
it's in the weekly plan. Under Wednesdays, I know where the link is.
Okay. Thank you.
Uh-huh. All right. Well, unless anybody has any questions.
We have 2 classes left.
Yep. We have 2 classes left. Monday and Wednesday.
That's crazy.
It is. Also, I went up to the school on Tuesday, and I brought home all my Diet Coke and Mentos supplies.
Yay.
Yay! So,
Miss Baskin.
yes.
A couple of weeks ago, you said that the College Board sent us an email to see if we're gonna take the test. I never got that email. Do I need to respond to that email to be able to take the test?
No.
Okay, good. All right, cool.
Yeah, they were just trying to, number 1, gauge interest, and number 2, test out their communication settings.
Oh, okay. All right.
So, but I will say you need to make sure that College Board has the correct email for you in your My AP account, because they're going to send you your test day ticket
Oh, okay.
in an email. So,
All right. Thank you.
Anybody else?
No.
Okay. Love you all. Happy Friday.
Bye.
Same to you. Happy Friday.